Morning, everyone. How are we doing? Questions? While we wait for a minute till everybody comes in. No, we're good? Yeah, I forgot about that, Matthew. I don't know if I can. Yeah, okay. I can whip something up, I think. Yeah, I can do that. Yeah, midterms. Midterms are finished marking. I will release I'll release everything this afternoon. Average was a little bit under 72%, which I find quite low. The median, however, was 76, which means that half the class got over 76. So we have not looked at optimization yet. We'll do that after, we'll do that next week. All right, so let's do a here's the is it blurry for people or just Jennifer? Very good. All right, so here's the question, and let's introduce some variables here as requested. let's put an A here and a B there. In the hopes that this will be fine, where A and B are real numbers. And while we're here, let's assume, well, let's not assume anything. No, let's assume A is not 0. First question, what is the domain? I might as well take B to be not 0 as well. So A and B, not 0. Right, because if B is 0, the whole thing is 0. And that's not interesting. What is the domain here? Regardless of what A and B are, domain is all real numbers. Let's look at the X and Y intercepts. If X is 0, we see that Y is 0. And if Y is 0, if this whole thing is 0, right, you've got a product equal to 0. So one of the factors has to be 0. Either this is 0 or that is 0, which would mean Bx is 0, but B is not 0, which would mean X is 0. So either X is 0 or 4 over A. Thank you, Michael. Let's move on to the first derivative. What is the derivative? This is the product, so product rule applies. Differentiate the first one, leaving the second one fixed. Plus leave the first one fixed. Differentiate the second one. This is Bx to the 1/3. We are just doing graphing today as well, Elizabeth, right? While graphing, and we're going to discuss slant asymptotes, or sometimes referred to as oblique asymptotes. This is Bx to the 1/3. The derivative is 1/3. Bx to the negative 2/3 times the derivative of the inside, which is just B. Let us factor out. What do we want to factor out? We have Bx to the 1/3, Bx to the negative 2/3. Let us factor out the smallest power of Bx, namely Bx to the negative 2/3. This leaves us with an ABx. This is gone, well, maybe a 1/3, so that I can get rid of fractions here. So I'm going to need a 3 here. 3ABx. This whole thing is gone. So I have a plus ABx minus 4B. Or, if you prefer, Bs to the negative 2/3, 4ABx minus 4B. Again, Fine. Then we take an extra step and factor out a 4b, leaving us with ax minus 1. So we see critical points. X equals 0, where the derivative does not exist, and x equals 1 over a. Right, so the fact that we have these variables floating around doesn't make anything any more difficult, right? Let's draw a first derivative chart. And now we're going to have to write. And but let's not worry about that, Zoe. Let's not worry about that. Zoe's wondering how we're going to graph this. Let's not worry about it. Let's just do the work, see what happens. And you know, I mean, I made this up on the fly, so we might be in trouble. But well, I mean, the idea, Sean is suggesting, factoring isn't always as easy as I make it seem. What have we done? We have factored the smallest power of whatever we have in common. So here we have a bx, here we have a bx, factor out the smallest power. That's all we've done. And then we've combined what's left. And then you factor out whatever you have. So let's draw a first derivative chart. And there's a slight issue with the first derivative chart, right? What is 1 over a? Well, that's going to depend on what a is. If a is positive, then it's going to be bigger than 0. If a is negative, it's going to be less than 0. As Benjamin points out, a value like 0 can be both a critical point and a 0 of the function. Absolutely. Nothing wrong with that. And that's exactly what's happening here. So the only thing you have to worry about in your first derivative chart is where to put the 1 over a. So we're going to need 2 first derivative charts, right? First derivative chart, if a is less than 0, then a first derivative chart if a is bigger than 0. Because if a is less than 0, this is going to be less than 0. And if a is bigger than 0, then 1 over a is going to be bigger than 0. That's the only issue here. Yep, and as Benjamin points out, same logic with points of inflection. All right. So take a number less than 1 over a. Notice this is something squared, so it's always positive. We can neglect this. This is 1/3, always positive. We can forget about that. Now, what's going to happen with the b? Well, it depends what b is here. If b is negative or if b is positive. Right, so again, we're going to have to split this up into a few pieces. But, I mean, we could have been smart. So first of all, let me point out 0 and 4 over a if we come back to this, and we're being smart here, this is the same as cube root of b times ax minus 4 cube root of x. So this is probably what we should have done to begin with. We should have probably factored out this b, and we wouldn't have had to deal with it at all. Right? So if we had removed this, we could have just dealt with this, and that would have been the way to go. But it's a bit late for that. So since we didn't do that, we now have to split up our first derivative chart into a few cases as well. So here's the case: a is less than 0, b is less than 0. And what happens then? So positive, positive, negative. What happens here? If you take a large, so a is negative. If you take a large negative number for x, this is going to be a large positive. Minus 1 is going to be positive. So positive, negative, positive, positive. The whole thing is negative. And if you take something close to 0 here, but, well, just close to 0, I mean, this is always positive, positive, negative. If you take something close to 0, this is going to be close to 0. So minus 1 is going to be negative as well. The whole thing is positive. And same on the other side, right? If you take something close to 0 here, this whole thing is going to be close to 0. Minus 1 is still going to be negative. So positive there as well. What's happening here? Would you be able to write out how you initially factored out to get the 1/3? Well, I mean, I took out a 1/3 because I didn't want fractions. So I'm going to multiply this by 3. And here I've got something to the negative 2/3, and here I have something to the 1/3. Exactly as Michael suggests. So we have this, and if b was the opposite sign, so if a is less than 0 and b is bigger than 0, then instead of having a negative here, you're going to have a positive, so all the signs are switched. So this is going to be positive, negative, negative, increasing, decreasing, decreasing. Needless to say, well, I mean, not needless to say, but we should have pointed out here that we have a, since the domain is all real numbers, your function is decreasing and then increasing afterwards. We have an absolute minimum occurring at 1 over a, and over here we have an absolute maximum. I mean, was it an issue differentiating this? Seems like it was relatively easy, no? I mean, it's just the product, so product rule applies. and then a chain rule inside. Well, for sure it's local, right? But in this case, it's absolute because your domain is all real numbers. Your function is decreasing until you hit this point, and then increases afterwards. So it never comes back down to something less than that. Yeah, you have to be an expert in differentiation, right? When you look at a function, you have to know exactly what to do. Is it a product? Is it a quotient? What's going on? You have to know how to differentiate immediately just by looking. That's where you need to be in this course. Because afterwards, when we do Cal 2, if you're not an expert in differentiation, you're going to have a difficult time in Cal 2. Why did we use only A less than 0 and not greater than 0? No, we have to use it. We just did half. We have to finish that up. So here, let's look at the case where A is bigger than 0. And B is less than 0. What happens then? If you take a number less, so B is negative. So this is going to be negative. This is always positive. Very good. If you take a number close to 0, this is going to be close to 0. So this whole thing is going to be negative. So negative, negative, positive, positive means everything is positive. And same on the other side, right? Because you're still taking something close to 0. But now if A is bigger than 0, if A is bigger than 0, you take a large positive value of X, this whole thing is going to be a large positive. Minus 1 is still going to be a large positive. So positive, negative, positive, positive. So here you see that you have an absolute max occurring in 1 over A. And finally, if you do the opposite, where A is bigger than 0 and B is bigger than 0, then of course this changes from negative to positive and all the signs change. So here you have an absolute minimum. How would pulling out a B initially stopped all of this? Because you could have graphed when B was positive, and then the graph when B is negative would just have been the same graph but flipped about the x-axis. Right, in the same way that the graph of y equals x squared and y equals negative x squared is the same graph, but this one is flipped above the x-axis. Did I want to do that? Gonna need that right here. Right, so we could have done all the work for B bigger than 0 and then just flipped it. Here was the first derivative. 1/3 bx to the negative 2/3 times 4b ax minus 1. We are going to have to do 4 graphs. Absolutely. Maybe more. Yep. Maybe, well, we'll see. We'll see, but let's not worry about that. Let's second derivative. This 4b over 3 is just a constant, so let's leave that out. And then you've got a product. So product rule applies. Differentiate the first one. Times the derivative of the inside, leaving the second one fixed. Plus, leave the first one fixed. Differentiate the second one. Well, I don't know about 3 of these, but you should expect 1. Right? For sure, you should expect a graphing question. All right, so the usual, right? Let's pull out the 2/3 because to get rid of fractions. In fact, I don't need to pull out a 2. Let's pull out a 1/3 to get rid of fractions. And let's pull out the smallest power of bx, which is bx to the negative 5 over 3. What does that leave us with? This is gone, the 3 is gone, so I've got a minus 2b ax minus 1. I took minus 5/3 out of there, so I'm left with 1. There it is. Two finals on the same day is nothing to worry about. First of all, you have 3 days for this final. So it's not an issue. Thank you. Thank you. I was going to forget the 3. Thank you for that. Absolutely. Right? I mean, in normal times, it wouldn't have been unusual to have 2 exams in one day. Right? So an exam in the morning and an exam in the afternoon. So now if you have 2 exams in a 72-hour period, that's nothing. Absolutely nothing. All right. Let's finish that up. 4b over 9, bx to the minus 5 over 3, minus 2abx plus 2b plus 3abx. And here, minus 2abx plus 3abx is just 1abx. So if I factor out a b from there, ab plus 2. abx. Ah, Jesus. ax. Right, it's abx plus 2b and factor out the b. All right. Yeah, the final will be, you'll have the whole 72 hours. And then first of all, as JD suggests, there's too many things, but I mean, he or she ends with, it's impossible to coordinate for the profs. We're not in charge of the final exams. The final exams are governed by the exam office, so they make up the schedule. We have absolutely no control over that. And we're not allowed to make any special arrangements. They are in charge of everything. Minerva suggests the last class is, I believe, December 3rd. I'm not sure about that, but yeah. So let's finish that up here. So possible points of inflection: 0 or minus 2 over x. All right. Let me erase some things here. Yeah, exactly, right? I mean, I keep hearing people complain that we only have like 12 days of Christmas break, but the truth is we have a lot of days between the last day of class and the first day of exams. This is highly unusual, right? Because normally we end class and exams start 1 or 2 days after. So let's draw a second derivative chart. And again, this is going to depend on whether A is positive or negative. So if A is positive, then this is going to be a negative number. So minus 2 over A, 0. And if B is positive, all of these things are positive. If you take a large negative number for X, this is going to be negative. And A is positive, so a large negative number will make this a large negative number. So negative, 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 and everything else is positive. And if we take a number very close to 0, either on the left or the right, this is going to be close to 0, so this is going to be close to 2. If X is negative, this is going to be negative. So negative here. And if X is positive, this is going to be positive. So positive there. All right. So you see that you have points of inflection at both places. And if, well, I don't know why I did this completely different, but if, yeah, that's going to be painful. All right, whatever. If A is positive and B is negative, right? If B is negative, This is negative, that's negative, that's negative. So you have three negatives. In other words, all the signs change. So negative, positive, positive, concave down, concave up. Oh, what have I done? Concave down. So again, these are points of inflection. And if A is negative and B is positive, then this is going to be positive. And what are we doing? B is positive, so all of these things are positive. When X is negative, this is negative. And since A is negative and X is negative, then this whole thing is going to be positive. So positive, positive, negative, positive makes everything negative. And if you take something bigger than 0, but just very close, this is going to be close to 0. So this whole thing is close to 2. The B's are positive. This is positive. Everything is positive. And finally, a large positive number. Since A is negative, this is going to be a large negative. Everything else is positive. So negative. Almost done. How are we yeah, right. So Matthew was asking, how are we defining what is between negative 2 over A and 0? All I'm saying is take a number very close to 0 here. Very close to 0, but positive. This is going to be very close to 0. So in here, this is going to be close to 2. So positive. A number close to 0, but positive makes this whole thing positive. And that's all that's important. Finally, let me erase a bit of stuff here. Finally, if A is less than 0 and B is less than 0, again, 3 negatives here make everything change signs. So plus, minus, plus. So this is again, I mean, they're all points of inflection. All right. Ready to graph? Almost. Almost ready to graph. We need to know where to start and where to end. In other words, what is the limit as X goes to negative infinity of this? And what happens? Obviously, this is going to go to some sort of infinity, depending on the sign of A. And this is going to go to some sort of infinity, depending on the sign of B. Right? Let's be smart here. And let's rewrite this as A cube root of B times x minus 4 over a times the cube root of x. As x goes to negative infinity, this goes to negative infinity. This goes to negative infinity. So negative infinity times negative infinity is positive infinity. And so it's going to depend on the sign of this. So let's say AB times infinity. So if both A and B are positive, then it goes to positive infinity. If both A and B are negative, it goes to positive infinity. If one is positive and the other is negative, then it goes to negative infinity. And similarly, limit as x goes to infinity. All right. So now let's graph. I am slightly worried that we're not going to have enough room. So let's concentrate on two graphs only. Let's take the one where A and B are both positive. And let's take one where A is negative and B is positive. Shall we do that? It is a messy question, absolutely. But, I mean, luckily on paper, you have more than enough room. Here, I'm running out of room. So, what did we say? We'll take this one. Where both are positive. And we'll take the one where A is positive, B is negative. So where A is positive and B is negative. So let me erase the rest so that I have room to. And I'll leave the other two to you. Here we go. So if A and B are positive, what does the graph look like? If A and B are positive, this is positive, so the limit as x goes to negative infinity is going to be positive infinity. So we start at positive infinity. You better be decreasing. You better be decreasing. And if both are positive, you are decreasing all the way to 0. You are decreasing concave up all the way to negative 2 over a. So decreasing concave up all the way to negative 2 over a. And you know you're still positive because the only x-intercepts are 0 and 4 over a, so you haven't crossed the x-axis yet. After negative 2 over a, you are still decreasing, but concave down now all the way to 0. And you know that at 0, you're at 0. Now we've rubbed off the first derivative, but I'm sure you remember that we had a bx to the negative 2/3, meaning a 1 over x to the 2/3 with some constant b there. In other words, at 0, your first derivative did not exist. In other words, you had a vertical tangent line here. So you're going to have some sort of cusp occurring at the origin. After 0, you're still decreasing. Concave up now, all the way to 1 over a. So still decreasing. So not really a cusp. I was a bit hasty in saying that. But a vertical tangent line nonetheless. So decreasing, concave up all the way to 1 over a. At which point you are increasing, concave up, forever. And where's the forever taking you? A and B are both positive. Forever is taking you to infinity. And you see that you have an absolute minimum occurring at 1 over a. Exactly as expected. Here, your x-intercept is 4 over a. There you go. Very nice. And here you had a horizontal tangent line. Doesn't look like it, but it's the best we're going to do. And you had a point of inflection here and a point of inflection at 0 as well. Why is it a vertical tangent line? Because the first derivative was undefined, exactly as Michael suggests. Why isn't there one at 2 over a? 2 over a was not a critical point. Why would there be a... Did you mean negative 2 over a? But again, negative 2 over a was not a critical point. There it is. Let's draw the one where a is bigger than 0 and b is less than 0. And let me point out that in this case, this product, if a is bigger than 0 and b is less than 0, this product is negative. And so is this product. So both limits will be negative infinity. Right? Both limits will be negative infinity. Let's remember that. And let's graph the case where a is bigger than 0 and b is less than 0. Both limits were negative infinity, so we're starting at negative infinity. You better be increasing, and you are increasing, concave down, all the way to negative 2 over a. Again, you will not have crossed. You will not have crossed the x-axis. Increasing, concave down, all the way to negative 2 over a. At which point you are still increasing, concave up now, all the way to 0. Afterwards, you are still increasing, concave down now, all the way to 1 over a. And afterwards, you are decreasing, concave down forever. And where's the forever taking you? To negative infinity. You see that it's exactly this graph, but just the mirror image above the x-axis, right? Because here, this was when a and b were both bigger than 0. And this one is when A is bigger than 0, but B was less than 0, which you would have gotten if you had factored out a B to the 1/3 to begin with. How are we doing? Questions? Right, I didn't label points of inflection and vertical and absolute max and none of that. I'll let you do that, but you see that it's really the mirror image of this thing. And again, there are 2 more graphs to produce. I'll let you do those. But it's the same thing, right? So again, don't let this idea of extra variables throw you off. If you're comfortable with everything, there's no issue. The remaining 2 graphs will be mirror images of each other as well. Exactly. Because one of them is going to be for B bigger than 0, and the other one is going to be for B less than 0. Absolutely, right here, going off to negative infinity as well. Thank you, Jordan. Moving on. Definition. Given a function f, y equals mx plus b is said to be a slant asymptote, or sometimes called an oblique if the limit as x goes to infinity of f of x minus mx plus b equal to 0, or limit as x goes to negative infinity. Convince yourselves that this is really just a generalization of a horizontal asymptote, right? You know the limit to be the behavior of the function. So what we're saying here is that for large values of x, your function kind of behaves like this line. Or for large negative values of x, your function behaves like this line. That's all we're saying. On a graph, what are the implications here? If your function has a slant asymptote at infinity, then that means that for large values of x, your function kind of behaves like this line. Right? The limit is getting closer and closer to that line. Or on the other side as well. The 2 slant asymptotes may be different, right? You know that the behavior of your function for large values does not impact the behavior for large negative values. So the behavior could be different. There could be two slant asymptotes. There might just be one on one side. Who knows? Shall we consider an example? The question is asking us to graph Consider this. So let's graph. Let's graph. What is that? Well, first question is still the same page. 327. Let's start with the domain. What is the domain? Domain is easily seen to be all real numbers. Thank you. What about X and Y intercepts? If X is 0, Y is easily seen to be 1 plus E. If Y is 0, it's going to be difficult to solve for X here. So we're not going to waste any time on that. And we're going to right away go to the derivative. Let me point out something here. Let me point out, before I erase this definition of slant asymptote, the question obviously arises, when do we have a slant asymptote? Well, what we're saying is that the limits should behave in the same way, right? So you know the limit as x goes to infinity of this is either positive or negative infinity, depending on what m is. And same with this one. So if your function goes to infinity as x goes to infinity, or as x goes to negative infinity, then you should ask yourself the question, do I have a slant asymptote? And we'll discuss that with this example. And, as people are suggesting, we're going to ignore it for now. We're not going to ignore it forever. We will come back to this. But we're just putting it aside. First of all, it's essentially impossible to solve. So we're not necessarily going to solve for it, but we're going to address it momentarily. But for now, let's move on to the first derivative, which is minus 1 plus e to the 1 plus x over 3 times 1/3. That's very odd, but anyways, let's see what's going on there. What are the critical points here? you see that the derivative always exists, so critical points are going to be where this is equal to 0. In other words, where e to the 1 plus x over 3 is equal to 3. Take ln on both sides. X over 3 is ln 3 minus 1. So x is 3 ln 3 minus 3. Very well. Let's do a first derivative chart. Only one critical point. 3 ln 3 minus 3. Which is bigger than 0, right? Right, because it's 3 times ln 3 minus 1. And ln of e is 1, so ln of 3 is bigger than ln of e. So this whole thing is bigger than 0. Go back to your derivative, and if you, well, in fact, no. If you plug in 0, this is e over 3, which is less than 1, right? 2.71 over 3, so something, well, less than 1. Minus 1 is going to be negative, which means your function is decreasing. Then if you take a large positive value of x, this is going to go to infinity. E to the infinity is infinity. Infinity divided by 3 is infinity. So very large, minus 1 is still a very large positive number. There you go. We have an absolute minimum occurring at 3 ln 3 minus 3. Move on to the second derivative. This is easily seen to be 1 over 9 e to the 1 plus x over 3. Elizabeth, I believe you asked that question earlier on the previous example. So you tell me, how do we know it's an absolute minimum? Of course, it's a local minimum as well, right? But absolute is more important here. Your function is decreasing. First of all, the domain was all real numbers, and that's very important. Your function is decreasing all the way to 3 ln 3 minus 3, at which point it starts to increase. And it never comes back down. It never comes back down. So, yeah. So it never becomes less than what it was at that point. Here, possible points of inflection, everyone? What are the possible points of inflection? So we know that because the domain is all real numbers, exactly that. No points of inflection, thank you, Michael. No possible points of inflection. Let's draw a second derivative chart. Labeling our possible points of inflection, there's nothing to label. Plug in any value, and you'll see that it's always positive. Let's look at the limits. We want to know where to start, where to end. So what is the limit of our function? As x goes to negative infinity, what is happening to x over 3? X over 3 goes to negative infinity. Negative infinity minus 1 is still negative infinity. E to the negative infinity is e to the negative infinity is 0. Thank you, Michael. This part goes to 0. 1 minus negative infinity is infinity. So this limit will be infinity. But just as important, we argue that this goes to 0. leaving you essentially with just this thing, the 1 minus x. Your function is going to behave like a 1 minus x, which is a straight line. You have a horizontal asymptote, we have a slant asymptote here. Because if you subtract that function, if you subtract that straight line, right? If you subtract that mx plus b, these things cancel, and we just saw that this limit was 0. And that's really the definition of the slant asymptote. Your function behaves like this. What about limit as x goes to infinity? Is the mx plus b in the function in all cases? Short answer, yes. Long answer, sometimes it's hidden and you don't see it. I'll give you an example in a moment. What happens here? As x goes to infinity, this goes to infinity, e to the infinity is infinity. This goes to negative infinity, so now you have infinity minus infinity. Absolutely, Michael. What are we going to do? Well, we have to manipulate in the hopes of using L'Hopital's rule. And what's the manipulation? Anyone? Anyone? What if this was a question on the final exam? Factor out? Not so much. No, because it's not multiplication here. If it was multiplication, that would be the way to go. But it's not multiplication. Instead, it's addition. I'm going to suggest factoring out an e to the whatever you want to do, either x over 3 or 1 plus x over 3. Factor out your leading term. Factor out the dominant term. And what is dominating here, right? I mean, you have x, but you have exponentials. So the exponential, as you may know, gets larger and larger much faster than x. Factor that out. What does that leave us with? 1 minus x over this business. Plus 1. And now, as x goes to infinity, let's just look at this part. This has the form infinity over infinity. So now we can do a L'Hopital's rule on that business. See what happens. Let me just remind ourselves, if x is 0, y is 1 plus e. Remove that. So let's look at this thing as an aside. Limit as x goes to infinity of 1 minus x over e to the 1 plus x over 3. which has the form infinity over infinity. So we can apply L'Hopital to this. Derivative of the top, derivative of the bottom. And as x goes to infinity, this goes to infinity, e to the infinity is infinity. So we have a 1 over infinity, which is 0. Absolutely. Thank you. So this part goes to 0. So the stuff inside the bracket goes to 1. This goes to infinity. E to the infinity is infinity. The whole thing is infinity. Which might lead you to believe that perhaps we have a slant asymptote here. It's possible, right? This is the situation where you might want to look for a slant asymptote when your function goes to infinity or negative infinity. But let's be smart here. And in the same way that the 1 minus x went to 0 when you divide it, if you were to subtract an mx plus b and factor out an exponential from the whole thing, right? In the same way that the 1 minus x went to 0, the mx plus b will also go to 0. By L'Hopital rule, exactly the same, right? If you have mx plus b instead, then the derivative is just m, and m over that is still going to be 0. So even if you do subtract any kind of line, the limit is never going to be 0. It's always going to be infinity. So no slant asymptote here. Asymptote. So Slant, as Slant suggests, oblique asymptotes can only take the form of a linear function. You could extend this to quadratics, cubics, degree 4 polynomials, blah, blah, blah. But the word slant asymptote is only for, the word slant asymptote is only for lines or oblique asymptotes. And he's asking, how do we decide to add mx plus b? All I'm saying is since this limit was infinity, we could search for a slant asymptote, right? That's exactly the situation when you would search for a slant asymptote. Well, Slant, you can define an exponential asymptote, and then you'd have one here, exactly. So you search for a slant asymptote when you have a limit of infinity, which we had that here. So, but I'm saying, instead of redoing the whole thing, let's be smart. And if you just throw in a minus mx plus b here and do exactly the same as you did, because you see, here you had a line, and when you divide it by the exponential, that whole thing went to 0. And it's going to be the same thing if you have an mx plus b instead of just 1 minus x. I'm not saying that it is mx plus b. I'm saying that the work would have been exactly the same. So in the same way that the function 1 minus x divided by this goes to 0, the function mx plus b divided by that will go to 0, which means that you don't have any slant asymptotes. All right, so let's put everything together. What are we saying here? Here we're saying that this limit was infinity and no slant asymptotes. Let's graph. Where are we starting? Limit as x goes to negative infinity was infinity, but we saw that we had a slant asymptote of 1 minus x. So if you graph that, 1 minus x, you know what that looks like. And here, for large negative values, the exponential is always bigger than 0. So you're just slightly above, you're just slightly bigger than this. So we're starting at infinity, but just slightly above that line. If it's my understanding some of you are still not sure about the fact that we have no slant asymptotes here, let's put that aside. Let's finish the graph and I'll come back to that and explain it in complete detail. So as x goes to negative infinity, we do have a slant asymptote, namely the 1 minus x. So we drew the graph here, y equals minus x plus 1, right? Straight line with negative slope, going with y-intercept 1. And for large values, your function is very close to this, but slightly larger because this is positive. All right, what's happening? We are decreasing concave up all the way to 3 ln 3 minus 3. So decreasing concave up all the way to 3 ln 3 minus 3. And here we are at 1 plus e, the y-intercept. All right. And after 3 ln 3 minus 3, we are increasing, still concave up, forever. And forever is taking us to infinity. There you go. Absolute minimum here with a horizontal tangent line. That's it. If he's asking why is it above the horizontal asymptote, what function are we looking at? Right? The function we're graphing is 1 minus x plus e to the 1 plus x over 3. And this is always bigger than or equal to 0. In fact, it's always bigger than 0. So this whole thing is going to be bigger than or equal to 1 minus x. The exponential is always bigger than 0. So the exponential plus 1 minus x is going to be bigger than 1 minus x. Here's a question. does y equals 1 minus x plus e to the 1 plus x over 3 have a slant asymptote? As x goes to infinity. That's the question we want to answer. All right. Might have answered it too quickly over here. So let's take our time and see. Let's see how to answer that. So we ask the question, is there a line such that the limit as x goes to infinity of your function minus that line is equal to 0? That's the real question, right? That's the question we're asking ourselves. Is there an mx plus b such that when you subtract it and take a limit as x goes to infinity, you get 0? We're going to do the same thing we did before. We're going to factor out the exponential. Right, so let's just look at this limit. Factor out the exponential. Is everybody with us? Is everybody with us? Questions? We saw that this goes to 0. No, well, probably not. We saw this goes to 0, and I suggested this was going to go to 0 as well, but I mean, perhaps this might have been lost on people. So let's look at it. If you look at this limit, this has the form infinity over infinity. You can do a L'Hopital's rule. And you get an m over e to the 1 plus x over 3 times 1/3, whose limit is easily seen to be 0 again, regardless of what happens, regardless of what m is, right? So in the same way that this went to 0, I claim this goes to 0 as well. So the stuff in the brackets goes to 1. And this goes to infinity. So the answer will always be infinity. It's never going to be 0. So no slant asymptote. Better? Anyone? How are we doing here? We want to take one more minute to see a slant asymptote. Matthew, can't it be 0? No. No, infinity is not every number. You can think of infinity as a number that, well, first of all, it's not a number. But in some cases, you can think of it as something that gets larger and larger nonstop. So, I mean, you're very far away from zero. Exactly. Example. Here's the last question. Well, Yusra, I think this question will answer that. Right? I mean, well, no, maybe let's answer Yusra's question first. You can do the same thing. You can answer the question as x goes to negative infinity in exactly the same way. This is the question now, as x goes to negative infinity. So is there a line such that this is equal to 0? That's the question. But now, as x goes to negative infinity, this does not go to infinity. This goes to 0. That is not the dominant term anymore. So you're not going to factor it out. Instead, as x goes to negative infinity, this goes to 0. So what are we left with? This limit is what? Well, I mean, so let me not, well, I mean, it does go to 0, but I mean, you never want to take a limit of part of it. So let me put it up front. Let me combine the x's here. This is going to be 1 minus b. And minus, if I factor out a minus x, I get a 1 plus m. Right, so we're just doing it from the definition. Right? So limit as x goes to negative infinity. Now, as x goes to negative infinity, this goes to 0. So that's not of any concern. If 1 plus m is not 0, then this limit will be some sort of infinity. Right? It's going to be infinity times 1 plus m. So if 1 plus m is not 0, then the limit is going to be some sort of infinity, which you don't want. So you need m to be negative 1. And if m is negative 1, this is 0, so this whole thing is gone. And if x goes to negative infinity, this goes to 0. So we're left with a limit of 1 minus b. Just this constant. But you want the limit to be 0. So b has to be 1. And there you go. You have your slant asymptote. Which was mx plus b. We just worked out that m has to be negative 1 and b has to be 1. Negative 1 plus x, negative x plus 1 is your slant asymptote. Consider this. Same question here. Does this have a slant asymptote? We're going to answer it in exactly the same way. Is there a line mx plus b such that this difference is equal to 0? Right, so is there a line such that the limit as x goes to infinity of your function minus the line is equal to 0? That's the question we want to answer. And we'll answer this one together and we'll end with that. I will let you do the same thing, but when x goes to negative infinity, right, because you could have one on one side and not on the other, or you might have the same one on both sides, or two different ones. So it's really very important that you test them independently. Well, what are we going to do here? Whatever you want to do. Maybe common denominator? Sounds like a good idea. Right, so this is the question we're trying to answer. Put everything over common denominator. Expand. So mx cubed minus 2mx squared minus mx minus bx squared minus 2bx minus b. Maybe we can expand the denominator as well. And now let's group things to make it nicer. You've got an x cubed, so 1 minus m x cubed, x squared, so minus 2m plus b, x squared, minus m plus 2b, x, and a minus b. There it is. And what is our hope here? Our hope is that this limit is equal to 0. That's what we want. Now take a step back and look at what's happening. On top, you have a polynomial of degree 3. On the bottom, you have a polynomial of degree 2. You know what's going to happen, right? I mean, first of all, you're going to get infinity over infinity. You're going to differentiate once, twice, possibly. And if you had an x cubed on top, you'd be in trouble. If you had an x cubed on top, you could differentiate twice. Here you would get a number. And here you'd still have an x. And as x goes to infinity, the whole thing would be infinity. So you cannot have a cube. You cannot have a cube on top, which means that the coefficient of x cubed had to be 0. In other words, m has to be 1. And if m is 1, this is gone. But if you have a square, you cannot have a cube on top, because if you, right, I mean, you have infinity over infinity, differentiate once, twice, and the denominator is gone. The denominator, the derivative, the second derivative is just 2. Whereas the derivative of x cubed, when you differentiate twice, you get 6x. And then the limit would have been infinity. So you're in trouble. So you need 1 minus m to be 0. In other words, you couldn't have a cube to begin with, or else the limit would not be 0, and that's what you want. The limit would have been infinity. So m has to be 1. But in the same argument, if you have a square on top and on the bottom, when you differentiate twice, both become numbers. And if you want the limit to be 0, this number had better be 0. So we can't have the square. In other words, 2m plus b has to be 0. But since m is 1, b has to be negative 2. Elizabeth, if you differentiate twice, the denominator becomes constant, whereas the numerator, you still have an x. So the limit's not going to be 0, but rather infinity. And if you had a square on top and a square on the bottom, when you differentiate twice, the derivative is going to be, the limit's going to be a number, namely 2m plus b. So we need that to be 0 as well. In other words, b needs to be negative 2. And in both of these cases, the cube is gone and the square is gone. But now you have a polynomial of degree 1 divided by a polynomial of degree 2. If you do L'Hopital's rule once, the limit is 0. And there you have it. So x minus 2 is the slant asymptote. Let me take 1 more minute to show you something. We have x cubed over x squared plus 2x plus 1. This is the function we started out with, right? I'm letting you do the minus infinity. Seelan, I'm not sure where your mistake was, but let's verify our answer using a different technique. This is the function we started out with, right? Let's do long division. What must we multiply to x squared to get an x cubed? We need an x. x cubed plus 2x squared plus x. If we subtract minus 2x squared minus x, bring down to 0. And repeat, what must we multiply to 2x squared to get a minus 2x squared? The answer is minus 2. Minus 2x squared minus 4x minus 2. And if we subtract this minus this, is a 3x. This minus that plus 2. What are we saying? We are saying that this business is actually x minus 2 plus the remainder over the divisor. And now you see it. This is your slant asymptote. Because as x goes to infinity, this goes to 0 by a quick L'Hopital's rule. And as x goes to negative infinity, so to answer Matthew's question, as x goes to negative infinity, this also goes to 0 by a quick L'Hopital's rule. No. This function works on both sides. Right? If you get rid of this, this goes to 0 as x goes to plus or minus infinity. So this minus that, which is just this, goes to 0. Well, I mean, here you can use long division. But in the first example we did, long division did not apply. So these are just nice tools that you can use to find the slant asymptote. How are we doing here? Am I making the slant asymptote harder than it actually is? Questions? All right, I think we've spent more than enough time. Thank you all for coming. I will release the midterms this afternoon, and I will see you guys next week. You guys have a good weekend. See you then. Seelan, I'm not sure what happened, but try it again. Don't look at your work. Just try it again. I'm sure you'll get it right. If not, you can email me. Lecture is over. You guys have a good one.